Welcome to this second video. We left yesterday talking about some things, Masonry structures, Abaqus modeling, etc. And I would like to give you a small example from the beginning to the analysis, to the end of the analysis of what I would like to talk about. A pretty academical example, I must say, but an example related to a real world case. I do have some pictures here I took 2 months ago about a work that I have done. This is the attic of a 100-meter square building. This is the first story, the second floor then, and we do have those columns, those masonry pillars with a wooden roof made with main beams, secondary beams, and hollow bricks called tavelle in Italian. Hollow bricks should be the English term for them. And we had to remove everything, starting from the roof, pillars. We retrofit the story, and we design a new concept of the roof with steel columns, steel beams, and wooden beams too. And some laminated timber panels above the secondarily wooden beams. So this is a classic attic. Many of these I have seen many of these in all Italy, typically of the reconstruction after the Second World War. Very many attics are made like this, and what I would like to show you is that the central masonry columns are made in full bricks, as you can see, and horizontal mortar beds, some vertical beds too. Those are hollow bricks, the full ones, the hollow, again the hollow called tabelloni, and the secondarily wooden beams just lay upon those tabelloni. They do realize the eave like this, the eave with the hollow bricks we've seen earlier, bricks as the ground floor, and we have some things to talk about. Okay, so the central columns are made in full bricks, I said, and they do discharge the load, the loads that come from the roof to two parallel walls at the ground floor, made also with full bricks. Those ones instead, wooden column and mixed full and hollow bricks, are not discharging on the under-level structural walls, but on the story instead. This is a reason why we demolished everything and we came up with a new conception, a new design of the attic. We can move on. The eaves, a crack, an interesting one. Oh yeah, this is a jump on the roof level called cartella, made in bricks. Okay. We have removed some external layer to see how were made the ground level walls. Here we are. Okay, this is the jump that the roof made. This is pretty interesting because this is a classical thing in Italy, I would say in Tuscany. This is a beam made of bricks. This is a masonry beam made with hollow bricks and some mortar bed to level this plane, to put some more bricks on. And inside of these hollow bricks are like some rebar, iron maybe, or steel rebar, which run from the beginning to the end of the beam, and they usually are on the top of the beam. That's pretty unstable, very unlikely to seismic safety, related to seismic safety. And I've seen many examples of roofs that collapse because one of these bricks reach its limit state, the fractures of it. And this cartel was this small wall, this small brick jump was then made again as a non-structural element. Okay, so I would like to model about the cracks. That could be a bit useful. Okay, here we are. There is a wall which runs from the main facade of the building, which is this one, which is higher than the roof plane, and it is made with full bricks. This wall continue to this level, then this wall over here, and then we reach the back of the house. This is the put and hollow wall we have seen earlier. Here we are. This is the wall with full bricks, but this wall at some time it interrupts, and then this is a jump of the wall. There is another wall, no picture of it. Let's see. No pictures, maybe earlier. Yeah, you can see this jump from the wall above, And this wall over here is made with hollow bricks. Then what happened? Those bricks are not clamped between each other. And then a fracture occurs. As you can see, hollow brick on the left. Okay, so we're going to model some masonry columns in Abaqus to understand how to use this academically based software to do some analysis. So then, first of all, Italian bricks. We are using this kind of brick, a full brick. The height of the brick, a classical Italian brick, 55 millimeters. The base, 120 millimeters, and the length, 250. These numbers are easy to remember just because 2 times the height plus 10 millimeters, which is the regular thickness of the mortar bed, gives this length at the base of the brick. And again, 120 multiplied by 2 plus 10, 250. Okay, so first things first. I'm not going to tell you anything about the main view, the commands. I would like to, as I said on the previous video, getting the hands dirty and understanding by trial and error. That could be long, but I assure you it could be definitely longer to learn first reading the Abaqus wiki, which is a mess, and then apply. We do begin with the part. The parts are the smallest item that is going to build our assembly, our structure. So I like to begin modeling the parts in AutoCAD and then import them on Abaqus, because I do not like at all the Abaqus CAD. Okay, so we can begin setting a new layer called brick. We also create mortar bed vertical and mortar bed horizontal. Then the brick. Orange, mortar bed yellowish, and then we are going to apply a load, a displacement load, using a steel plate, a rigid body. Then we do set steel plate. Okay, first things first, we start with the brick, and I'm drawing in millimeters. Abaqus does not have units of measure. You have to understand how the various units relate to each other with a criteria. Then, okay, so we start with $250, $120. Okay, good. I'm going to extrude this of 55 millimeters. So we do have our full brick. 55, 120, 250. Then we have the mortar bed between two bricks. The mortar bed, the thickness of it is 10 millimeters, and the plan dimension of it are 55 per 250. Vertical mortar bed. $250 for 55. We're going to extrude it of 10 millimeter. Now, like to rotate this works very bad sometimes. Okay, I select an axis then. Okay, then we have the horizontal mortar bed, which acts on the basis of two bricks, 120 plus 10 plus 120. Then 250 by 250. And again, let's extrude it to 10 millimeters. We do have then our steel plates. We can use the same 3D model. We just adjust the thickness okay, 20 more. So this is 3 centimeters. No, it doesn't work this way. Okay, 30. Good. Steel plate. We have everything we need to build our full brick masonry column. Now we do save this as a test, then we export as a SAT file all the solids we made. Okay, let's quit. Let's open Abaqus and then import, file import part. From the desktop we do select the SAT file we just saved. Part name, let's put tests, import all parts, create of course individual parts. All of the 3D solids are 3D deformable items, and the scale, we are not using any scale, we want millimeters. Okay, so we have in model 1 4 parts. The number 2 we rename it brick. Mortar bed horizontally, mortar bed vertically, and then steel plate. Okay, second thing to do is assign a property. Material manager, from here we do assign some materials. We create a new material, brick. Density, of course, and we do assign an elastic behavior. We are trying to run an elastic analysis. So we are not using any plasticity, we are not using a thermal electromagnetical analysis, just adding a density and an elastic behavior. So density. Abaqus works, as I said, with non-units of measure. We have to start with a unit. For example, as for length I'm using millimeters, and for forces I will use Newton per millimeter square, meaning megapascal. And for density, following this criteria, I must use ton per millimeters cubic. Meaning of, if I am defining a brick which has a weight of 1700 kilograms per meters cubic, I do have to multiply this one by 10 at minus 3 to get ton meters cubic, and then this one by 10 at minus 9 comprehensively minus 12 to get ton millimeters cubic. Okay, so we are going to do this 1700 10 at minus 12. Elastic behavior described by the Young modulus from technical sheets you can find on the market, full bricks with 8000 megapascal as Young modulus and a Poisson ratio of 0.2. Then we create a mortar material in the same way, assigning a density. The mortar on the market is dry, you have to mix it up with some water, and then it goes through the bricks, above, under, and it solidify. A mass density of 1850 kilograms per meters cubic, elastic behavior of 2000 megapascal, and a Poisson ratio of 0.25. Now I'd like to remember you that the mortar has a Young modulus and a lower than the full brick modulus and the Poisson ratio higher. That means that the mortar deforms itself higher than the brick does. And according to one of the first analysis theories for the masonry walls, the theory of Langsner-Francis, the mortar is suggested in a 3-axial state of compression, which means that the failure of the structure we are analyzing 99% of the times is not caused by mortar failure, which moves in a hydrostatic axis of the criterion we are choosing for the mortar. That's a reason why you can perform elastic analysis in the mortar instead of plastic. Of course, you have to check displacement and forces, tension that go on the mortar for not getting not convergence results at the interface between bricks and the mortar. Okay, then mortar, and then steel. We are assigning the classical density and also an elastic behavior. Okay, now we have to communicate the materials and the parts. We are doing this with the sections. Create section. Section brick, solid, homogeneous solid, material brick, no plane stress strain thickness used. Then we create a mortar section, solid, homogeneous solid, made with material mortar, and then we create a steel section for the 2 plates we will be using, solid, homogeneous, steel material. We have to assign these sections to the paths. So we do open the brick path, section assignment, select the regions to be assigned a section. Here is the brick path. I'm going to select and highlight the brick. Done. Section brick. Type solid homogeneous material brick. Okay. And it becomes blue. Let's close brick and do the same things with horizontal mortar bed, section assignment. I am selecting a region here, a region, this one, done, mortar, okay, blue, vertical mortar, section assignment, select a region, done, mortar. Steel plates, section assignment, click on the plate region, done, steel section assignment. Okay, we have done with the part and the property module. We now move to something interesting, which is the assembly module. We have to assemble the parts, and we can do like this. First of all, I have to create an instance. Create an instance meaning I have to import the parts inside my assembly module. So I'm going to create an instance from the parts, of course. I am going to select just the brick, instance type, dependent, independent, auto offset. Okay, so what is this? Dependent instance meaning mesh on part, meaning that the mesh I will use on this brick will be replied to every other brick parts. Independent, if I would like to understand what happens in just one brick, I have to choose this one and then mesh all the bricks except the one I wanted with a different mesh, a higher mesh, than a really low level, very complex mesh that I will use for the bricks I want to analyze. I am going with dependent, and this auto software set from other instances means that if I'm going to import more items, I can offset all of them to not compenetrate and use them, move them, modify them in an easier way. I'm going to pick up brick dependent. Okay, so the axis X, Y, and Z are okay for me right now. This is my first brick. I'm going to import then a vertical mortar bed. Apply. I have to rotate this instance over here, then rotate instance, select, done, select an axis. I'm not going to select an axis, I'm going to select 2 points working for an axis. So I am rotating this solid accordingly to the x-axis. So I'm going to put 90 degrees, enter, done, and now I'm going to move, picking this region, select this point over here and this one, done. Now I'm going to call another brick and set apply, and I'm going to move this brick here, done. Okay, Now I can call for a mortar horizontal bed, also dependent, and translate this here. Done. Okay, so I can do this in two ways. Create instance, brick, auto offset dependent, apply. I have to rotate this brick accordingly to the picture I have showed you earlier. I'm going to select rotate instance, this instance, done. Vertical axis, vertical points taken, same Z and Y, angle of rotation 90 degrees, done. And now I am moving this here. It does not compenetrate. The mortar bed. We have to rotate it twice. I clicked on OK and not on done, not on apply, sorry, so I can rotate this again. Selected, 2 points as an axis, done. Now I did close the command, translate, this point goes here, done. Okay, now I have to move this one up here, not by an import, for example. I'm going to ask, I know, but tools, query, distance between this point and this point. So first click, second click, 65 millimeters. Then linear pattern. I would like to select this, done. I can only replicate it in its plane, XY plane. Now, I would like to set one offset in this direction, more spaced. Okay, so I can move it freely here. Now let's assume I do have to replicate all of this, and I can replicate only on the XY plane. I have to rotate this done. I have to rotate through an X parallel axis, and the Z is going on the Y, so minus 90. Done. Okay, here we are. I want then to get this distance 130 millimeters. I want then to replicate all of these in the direction 2 here it is by 130 millimeters. As you can see, if I do put 132, it's a small gap, so the number is correct. How many times? Let's say 4 times. Okay. So my pillar is quietly done. We have just to rotate back all of this. Done by this axis. So the Z is going to Y, am I right? The Z is going to Y minus 90. I'm getting it. Have to change this too. Okay, so I would like to move then this to the origin. Translate. Select everything. Done. I click this node and I set 0, 0, 0. Enter. Done. Here we are. So I have to put the plates. Steel plate. Apply. Translate from this point to this point. Done. I have to remove this mortar bed over here. How can I do that? Not that easy. I don't know another way, so if you do know, please tell me. I have to navigate through the assembly, 33 instances, and find this one. How can I? This is a mortar bed, is an horizontal one, not this one, not this, no, 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 which is this? Oh, here it is. Right click, delete. I can replicate this then. Query distance between, oh shit, this and this, 540. Replicate this. Not needed the distance. Done, because I cannot replicate this through Z. Then translate to here. And now let's translate it again. Okay, the assembly is done. We have to move now in the mesh module. I mean, you can do these things, the mesh first and the assembly, do whatever you want. Just practice and check the pros and the cons of it. The mesh. I would like to do a good job, so I would like to cut the mortar beds and the bricks too in the thickness with 3 meshes. Now I'm using the hexagonal mesh over the tetrahedral one. It is more accurate, VX of course. The classic 8 elements. I can only select the 20 elements X mesh, X element, but we'll go with the 8. Now, mesh. I'm meshing through the paths, so I'm going to pick path, brick, and assign a seed for the mesh. I'm going to pick up a 50 millimeters. Curvature control, I always set these things by default. Apply. Here are the mesh nodes. Mesh part, yes. That could be nice. Could be nicer though. Let's say that I'm okay with it. I'm not going to investigate any further, but I do want 3 elements through the thickness. Then I pick up seed edges. I'm going to choose this edge done by number. By number 3. Apply. Delete the mesh I have done earlier. I see a mesh constraint here. Mesh part again, yes, here we are. Not beauty this mesh, I know this length is more than double than this one, but it's okay for the purpose of this video. Horizontal mortar. We set 50 as a global seed, but we want to control this edge with 3 elements. Here we are. The vertical one, 50. The edge, the mesh, very ugly, and then the steel plate. Steel plate is not needed that much to be 3 mesh elements over the thickness. Then I just pick up a 50 and that's okay. So if I do go to mesh again, not to the part but on the assembly, here we are. Now do not be worried by the thing that the nodes of the mesh do not connect each other. It's not a problem in Abaqus. I mean, I read something like this. It's not like SAP 2000 and other finite element software. Now, the mesh is done. We have to set some steps in the analysis. Let's manage the steps. So the analysis starts and there is an initial step. We're going to create another step where we do apply our load. So we create a displacement step after the initial step. The static analysis, of course. Let's continue. description not needed. Non-linear effects, let's turn them on. Incrementation, other, and basis. Okay, so the time period of the analysis that we're going to run. Let's put 100 seconds. This is a typical time I do always put. Incrementation. Okay, so we're not going to put a force or a displacement just bang. We have to let the software find the differential equation solutions, and they have to converge. So maximum number of increments 100. The first step start with a 1 point E at -2 with a minimum step for convergence 1 point E -4 and a maximum step, of course, 100 that we put earlier. Other. I never touch anything about these. Let's go further. Displacement, time 100. Okay, so we're going to the interaction module and we're going to set some things first. Load. Some restraint. Okay, let's say that the basis is fixed. We have to set as an internal restraint a constraint then. Let's create one of them. Create a lower plate rigid body. Rigid body. Continue. We are missing the reference point. What is a reference point? It's a control node we're going to assign. Assembly. This button over here. Let's click a little bit more and then go to create atom point midway between 2 points. Let's pick this one and let's create a point in the middle of those and here. Cancel. Okay, those 2 points over here will be my reference point for the constraint I'm going to put. Interaction. Constraint manager. Create. Lower plate rigid. Rigid body. Continue. Now let's select the body elements. Let's pick them up. Here we are. Done. A reference point. Not taking it. Why? Because this is just a point, not a reference point. So we have to go back on the interaction module and set a reference point. The one for the lower and the two for the one at the top. Now we can assign properly the rigid constraint. So I want that the first constraint would be lower plate rigid body. Continue. Let's pick a body. Yes, sorry. Done. A reference point. Good. This is a rigid body. And then create upper plate rigid body. Body elements picked. Reference point picked. Okay. So we have the rigid bodies. Now we also have a restraint over here, and this restraint on load create boundary condition. let's say encastre, step on the initial, symmetry, anti-symmetry, continue. Let's pick up the intradox of the plate, done, encastre. Okay, good. So we have the restraint, but how do the bricks interact with the mortar beds? We can go back to the interaction and find contact pairs. But before doing that, I would like to select some cells, 1 and 2, and remove them from the view. Okay. So find contact pairs. I would like to search through the display entities. Then include pairs within separation tolerance. Too much. 0.1 millimeter. Extend each surface found by angle. Okay. This thing, I don't want to extend the surfaces because the mortar beds are very thin. Name prefix CP, okay. Entities, it's okay. Pretty everything is okay. I don't want overclosed surfaces for convergence problems. I don't want to merge pairs. I want distinct surfaces. Now, let's find contact pairs. Here they are. We can assign some things here. A contact surface, a constraint for the entire surface, but we're going to, in linear elasticity, to have some convergence problem. For this purpose of this video, we're going to use a tie constraint. A perfect tie constraint between the mortar itself and the bricks. So we're going to enlight the surfaces. Okay, we're not going to do anything about the master surface, slave surfaces for now, not needed in this analysis. Type of interaction, select all, edit, tie constraint, and we can only go to select, nothing else. Adjust secondary surface, discretization surface to surface, which is okay, and we're going to select okay. Okay, then we have our constraints. Here they are. What we are missing actually is how the bricks and the mortar interacts with the plates. We can do that this way. Let's show all things up, and then let's go back to interaction module, find contact pairs, but I'm not going to put a tie constraint right now. I'm going to create an interaction property. Plates, everything else. I'm going to assign a mechanical normal behavior hard contact to prevent the compenetration, default, allow separation, just I do always leave the default things before learning very well what they do. Mechanical, tangential behavior, penalty with a friction coefficient of 0.6. Isotropic friction in all direction, no limit at the shear stress, elastic slip by default, and this contact property is the property I'm going to use, finding contact pairs, and again between the plate, brick 1, shift hold, mortar bed, brick 2. Done. I will deflag the same things I did before, and let's find contact pairs. I do have the master surface of the brick and the slave of the plates. Let's invert them just to be sure that no problems will occur with the plates contact. So this is the master surface and the slave, the master and slave, the master and the slave brick. And we also have two more surfaces which are already computed in the interaction tie constraint we did earlier. So I'm going to delete them. Interaction, surface to first surface contact interaction, sliding, finite or small. Let's go with finite. Please read the wiki about it. Discretization is surface to surface, property, plates to everything else. Adjust, I would like to adjust only to remove the oval closures between the surfaces. Surface smoothing, automatic smooth. Okay. The three interactions. Then we move here and we'll do the same. Find instances, pick the instances 1, 2, 3 and 4. Done. Find pairs 1, 2, 3, delete. Surface to surface, property plates, adjust, surface smoothing is okay, fini. Okay, good. We are missing now the load. I'm not going to use a force load. This because the displacement force function is not surjective, it's not bijective, and I really love to make displacement analysis accordingly to a great book by MJN Priestley, Displacement-Based Seismic Design of Structures, where he and Gian Maria Calvi and Michael Kowalski discuss about how far is better the displacement analysis instead of the force one, the force-based one. So we're going to do an analysis displacement control. Displacement, we're going to set as load. We can find it on load. Instead of create load, create boundary condition. Displacement, mechanical. Displacement rotation type, continue. Select a region I'm going to pick up the entire cell, which is a rigid body. Done. Okay, so global system U3 okay, strange, what's going on here? Displacement, no, move right, edit, oh, here it is, sorry. Displacement at the load, at the step called displacement, not at the initial condition. First of all, let's create an initial condition with the encastre, which propagates through the second step, which is called displacement, and we do apply a boundary condition called displacement 2. We're going to edit this. Distribution uniform, yes, U3 equal to -1, and the amplitude. Okay, we have to do this first. We have to say that a time versus displacement relation is needed, and a time of 1 second I'm going to apply a displacement of 10 on 100 seconds, meaning of 0.1 millimeter. If you would prefer sec millimeter, and then we can sum all of this, reaching here we are. So if I do put this scalar value over here, -1, and I am not going to pick up the ramp amplitude for the load, because this will start with 0 and then with -1 millimeter, I'm going to create an amplitude related to the axis steps I want to do. Create an amplitude, let's call amplitude 1, it's okay, a tabular amplitude, continue, span, step time, time/frequency, amplitude. So I'm going to select all of this, time 1 to 100, where the amplitude goes to 10, multiplied by -1, -10 millimeters. Paste. Okay. Select it. Okay. Wonderful. Now, we have done everything, I suppose. Let's go with the job. Create a job. Job 1, source model, continue. I'm going to put some gigs in it. Let's say 26 gigs, multiple processors, 8, and then we can run the job. Let's run the job, submit. Okay. Monitor. The analysis is complete, with some warnings. You have to check this up to understand how Abaqus thinks. For example, for type R, blah blah blah, adjusted nodes with very small adjustments were not printed. No problem at all. Adjustment was specified, sorry, but no node was adjusted more than the adjustment distance, which is 0. Okay, everything is fine. Blah blah blah. Blah blah. 16 nodes have been adjusted. Missing intersection with the respective main surface. I don't know what's this. Let's see what we have in the results. 4 node associate. Prescribe the nodes other than the reference node. No errors then. Okay, if I'm going then to open the temp, the ODB result of it, let's save it first. Temp test. Okay, open an ODB. In the folder, the default folder, the current work folder is temp. If you install Abaqus, job 1. So here we are. This is our Masonry column with our mesh. In the undeformed shape, let's see the deformed shape. Deformed, deformation scale factor 1. Okay. Great. Now let's go and see some qualitatively graphs. I would like to see the displacements first. The displacement along the z-axis -1, 10, +1, 10 millimeters. Zero, the encastre. The out of plane displacement then, it is heuristic because the y-axis grows this direction inside the monitor and decrease in this direction also outside the monitor through me. When I do put a displacement, a load, in the vertical direction of compression for the Poisson ratio, the Poisson effect, it goes larger in the orthogonally direction of the load, then these areas minus 0.5 millimeters and plus the respective plus 0.5 around that. And also on the U1, I suppose, yes. On the semi-axis, negative semi-axis X, -5 and +5 on the positive semi-axis X. So this is heuristic. Let's check some stress. Okay, as I said at the beginning of this video, remembering the Langsner-Francis theory, the mortar beds are under a 3-axial state of compression in this case, and the bricks instead are suggested to a biaxial state of tension. Is that right? Let's check. First of all, stress. The normal stress on the faces normal to Z, it's of compression everywhere, which is right. We do have that the vertical beds are compressed in absolute value lesser than the horizontal beds, which is right too. But what I want to see is what happens out of plane. S11. Okay, so S11 is the force per area unit, so the stress in this direction. We do have that this brick over here is under a tension stress, this direction. Which is true. Tension stress, and here, let me see, we have a compression here, we have a tension on the border with the mortar horizontal bed, if we do see S22 is the same, yes. Tension. This goes to tension related to the vertical masonry, yep. Okay, let's see also the minimum principle. Not appreciable, but we can see that the direction of the minimum principle stresses, which are this way and this way, are parallel where the fracture occurs in the bricks in this case. Remember, this is a linear elastic analysis. Let me see them again. Vx, tension, tension, and tension. Okay. The two. Tension and tension. Yeah, that's right. Because tension, tension, and tension on the major free face, then in the opposite direction, where the normal is S11, you are getting the tension on the maximum face instead of this one, because it goes greater the displacement in this way. And in fact, if staying here, if I do move on S11, what I'm going to see is a lane of tension here, a lane of tension here, a lane of tension here, and some mixed values in these cells over here due to the lesser area perpendicular to this axis, the x-axis, and due to the vertical mortar bed. Tension, 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 mixed values. The mortar bed is in tension in this way and is compressed, the horizontal one. Okay, so we have done, I do hope you enjoy a little bit this video, and we can discuss in the next few weeks about something more complex, something more interesting maybe. Thank you very much, everyone.